So we'll learn about cluster analysis in this video. So let me first show you the outline for this lecture. We'll start with the basic concepts, and then we'll go into the details of different types of clustering techniques such as K-means clustering, hierarchical clustering, and so on. We'll talk about how we calculate distance function, how do we standardize data before using it in clustering, how do we choose which clustering algorithm is to be used, and how do we evaluate the performance of clustering algorithm. We'll also learn a bit about how do we perform clustering using R programming. Okay, so these are the things we're going to cover in this particular lecture. Okay, so in machine learning we basically come across two types of learning algorithms. One type is supervised learning algorithms, and the other one is the unsupervised learning algorithm. Supervised learning is used for label data. So whenever we have a target variable, that means we have a label data, we use supervised learning algorithm. And whenever we have unlabeled data, that means there is no target variable, we just have the attributes or the features alone without having a target, then we use unsupervised learning. Okay, so that's the basic difference between supervised learning and unsupervised learning, and these two are probably the most popular learning algorithms, a set of learning algorithms we use in machine learning. Now clustering is an unsupervised learning algorithm because there is no target variable in clustering. Okay, you just have the attributes or the features of something. The clustering algorithm will simply group the data into different segments or different groups. Okay, it is not going to tell us that what is the label of each group or each segment, or what is the name of each segment or each group. So clustering is an unsupervised learning, and we'll learn more about how this grouping or clustering or segmentation actually is done by the cluster algorithm. So just to take an example, and that would be more clear, let's take a real world example. Google uses clustering algorithm to cluster or to club or to group similar news articles. News articles are not labeled. That means when you have a news articles, we do not know on what topic this particular article is. We of course have the title of the news article, but that doesn't tell much about the topic in which the article has been written. That means the titles could be different for each articles in different, for a particular article in different newspapers. Now what Google does is it scans through the entire web page for each news article and finds out the similar articles. Now it can't find out what exactly is the topic involved, so it doesn't know what the topic is, but all it knows is that these articles are similar. So here is an example. So we have this cluster of articles, and they are of similar types. Okay, so Unilever threatens to pull ads from Facebook and YouTube. Okay, so that's in the newspaper Guardian. In BBC News, it says that Unilever threatens to pull ads from Facebook and Google. Unilever threatens to pull ads from Facebook and Google. So we have articles being published in many different news sites, whether it's Guardian News, BBC News, Fortune, Quartz, The Times, and so on. So Google scan through these web pages, hundreds of thousands of web pages, to find out similar news articles. It of course will never tell us the topic on which the news articles have been written. It just groups them, and that's why it's an unsupervised, and it works on unlabeled data where we do not know what exactly is the topic, but we know that the topics are similar. Okay? And most real world data will be in unlabeled form, whether it's your text messages, whether it's your social media data, whether it is a lot of this data available on Google web pages, on blogs, on the comments on different social media content. Well, these data will be unleveled. So in real world, we have more unleveled data than the level data, and getting level data is very expensive. So clustering is very helpful whenever we have unleveled data. So another illustration of clustering. Here you can see three types of different data points. Now it is very clear to human eyes that there are three clusters of data, right? This is one, this is other one, this is the third one. Right? And we know it when we see it, right? But how does clustering algorithm finds out that there are three segments or three clusters of data sets or data points? Well, it tries to find the distance. It tries to find the distance. Let's say to see the distance between these points, like the points in, let's say this is circle 1, this is segment 1, segment 2, and segment 3. The distance between points, the black points, between segment 1 and segment 2 is quite large. But distance between each point within segment 1 is relatively much smaller, right? So what we are interested in is within cluster distance, and between cluster distance. That means within the cluster, the distance should be as less as possible, whereas between cluster, the distance between the points, different points or element of that cluster, members of that cluster, should be very high. Okay. So similarly, the distance between points between cluster 2 and cluster 3, or whether it's cluster 1 with cluster 3, is quite high, whereas between the points within the cluster is much smaller, right? And that's the basic idea or basic thinking about how the clustering algorithm works. And there are different variations of it, like how do we find within cluster distance and between cluster distance, and based on how we find these distances and based on how we come up with these segments, there are different sets of or different types of clustering algorithms, and we'll see a few of them. One more real world use, many retail companies, they want to group their products into different sizes, like an apparel company might want its t-shirts to be clubbed into small, medium, and large t-shirt. And given a set of features without having a label, if with the help of the feature the algorithm is able to find out the set of clothes which are very small, which are medium, and which are large, is also one example. In marketing, is very useful because marketing data do not have a label many times. You do not know much about what it talks about, but you have some data about customers or their products and so on. So you can have marketing segments, and then later on with expert judgment you can analyze this segment and sort of come to some conclusion. But many times marketing is where clustering is very useful. So different aspects of clustering. Clustering algorithms are of various types. Some of the popular algorithm uses what is known as partitioning clustering, hierarchical clustering, and we'll talk more about it in the next few slides. What is also important in clustering is what I was talking about in few slides before, that we need to measure the distance between points. And measuring the distance between point is important to know the similarity and the dissimilarity, because we want to club or we want to group similar elements or similar data points, and we want to differentiate dissimilar data points, right? So distance is a very important thing, and we need to use a distance function to calculate the distance between different points. So what is more important for us is to know the inter-cluster distance and the intra-cluster distance. Okay, that means distance between points of two different clusters, and distance between points within a single cluster. Okay, and inter-cluster distance should be maximized, intra-cluster distance should be minimized. And that's the algorithm, which is the core of the any machine learning, any clustering algorithm. Okay, so the first one and probably the most famous clustering algorithm that you will ever come across is the K-means algorithm, and we'll talk about it in detail, and then we'll go into other forms of clustering algorithm. Okay, so K-means is a partitional clustering algorithm. I'll talk about what is partitional clustering. Well, as the name suggests, it partitions the data into different clusters. Okay, so it's just an example. Let there be a set of data points. Okay, and let's say there are x1 to xn, so there are n number of data points. Okay, so what the K-means algorithm does is that it partitions the given data into k cluster. Okay, so n number of data points have been clustered into k clusters. A k is a real number, it cannot be a fraction or a negative number, right? K could be 2, or could be 4, could be 8 or 9. I mean, it could be any number, right? And each cluster should have a cluster center. We call that as centroid. That means that's the center of the cluster, and k is being specified by the user. And this is very important, that you only, if you perform K-means clustering, you are the one who is going to provide how many clusters are there or are present in the data. That happens to be one of the weakness of this algorithm. But if you're working in that data for a while, and let's say you are a marketing manager and you're working on a marketing data, then you know how many clusters are there in your data, but you do not know which data point belongs to which cluster. So K-means algorithm basically helps us knowing which data point belongs to which cluster, but it doesn't quite help to know how many clusters are there in general. That has to come from yourself. Okay, so how does this algorithm works? Well, it works in 4 steps. So in the first step, it randomly chooses k data points to be the initial centroid of the clusters. Okay, let's take an example. So let's say we have a set of points. Okay, so it randomly chooses, let's say we say that we know that k is 2. So there are 2 centroids. So here is one centroid, this data point is one centroid, and this data point is one, which we have chosen this randomly without being biased. Okay, in the second step, assign each data point to the closest centroid. That means here is a centroid and here is another centroid. Just calculate the distance and then see which data points are closer. Now you can see, and these data points are closer to the first centroid, these data points are closer to the second centroid. Okay, now you recompute the centroid after having the cluster. Now you have two cluster 1 and cluster 2. You recompute the centroid, and centroid can be computed by by taking average distance, right? So some other data point could be now a centroid, then the second step, maybe other data point became a centroid, and then you group the data points in different cluster. You keep repeating, okay, till the time there is no convergence. And what is the convergence criteria? In the next slide we'll talk about. Next few slides we have what's the convergence criteria. How do we know that the algorithm has converged? Okay, so that essentially is the way. So the way we know a convergence criteria is to see whether there is no reassignment of data points to different clusters. That means you do the iterations, right? I talked about the iterations, that in the first iteration you yourself, the algorithm will randomly choose the centroid, but the next step it will calculate centroid based on the existing cluster. Okay, and in iterate, keep on iterating, right? There will be a time when there is no reassignment. The first time, so I'll show you an example in the next slide, and that will be way but more clear. Well, there will be reassignment data points to different cluster in every iteration, but there will be a point where there is no reassignment. It's no changing. In the next iteration, it's the same as the previous, and that's when we realize that we have reached the convergence. And there is no minimum change in the centroid. That means the error term, the distance of each point from the centroid, is remaining constant in each iteration. It will obviously go down with iterations, but there will be a point when this is not going to change. So these are some of the convergence criteria that the algorithm uses. Here's an example. So we have set of data points. This is the first step, and we put through this clustering K-means algorithm. K-means algorithm chooses two random data point to the centroid, and accordingly it assigns data points to different clusters. So here is one data point, and second one is this one. So these are two data points chosen randomly, and remember, randomly. That means you only have provided that k equal to 2. That means there are only two clusters present. So there are two centroid. Now it calculates the distance and finds out that these many data points are in this cluster where centroid is this one. These are the data points which should be in another cluster. Now you recompute the centroid. That means now you don't have to do it randomly. The first time you did it randomly, right? Or the algorithm did it randomly. The second time it has to calculate the centroid by taking the distance of each point, and centroid is nothing but central point of a cluster, right? So this will be somewhere here. So here also this will be somewhere here. The centroid will be somewhere here because this seems to be the central point of the cluster. Okay, so just by calculating the distance of each data point within a cluster and taking an average, you'll be able to find out where exactly you end up having your centroid. Okay, so one of these data point will be again a centroid. Now this centroid has changed, right? So in the next step, in the next iteration, in the second iteration, you can see centroid is here and here. Previously we had here and let's say here, right? So this has changed now. The centroid has changed. If centroid has changed, the next step would be that you again calculate the distance and regroup the clusters. That means the nearby points will be in the nearest cluster. So this cluster, this data point is very close, but this is far off, right? So this data point should be in this cluster, not this cluster, right? So this regrouping will happen in the next iterations, and that's what it is. You can see, right? So the data point, so this data point I showed you, right? These two data points are part of this cluster, and these data points are part of another cluster, and that's what you can see here, right? There's a clear difference in the last iteration and this iteration. Okay, in the next step, you can see there's a clear difference. Then again the centroid will be calculated, and there isn't much change. Centroid is somewhere here, centroid is again somewhere here. Then you calculate the distance of each point and try to regroup the data points in a cluster, right? So each data point is closer to this one, so this is one cluster. These data points are closer to this one, so this is another cluster. But you see that there is no change. This is exactly what we had in the previous step, and you continue for a few more times. You see there is no change after that. After the first iteration, there is no change. That means we know that the algorithm has now converged, and we now finally have two clusters in place. Okay, so this is the way the algorithm works. That it works with iterations where there is a recomputation of centroid and reassignment of data points to different clusters, and only when there is no change in few iterations, then we assure that there is no change. How do we calculate the distance is a very important question to ask. Well, we all know about the Euclidean distance, that given as two different points, let's say x1 y1 and x2 y2, you can calculate the distance by taking the distance formula, like which is x2 minus x1 square plus y2 minus y1 square, and take this square root of that, and that's your distance, right? So that's the way we calculate. So this is the distance formula, and you can calculate. This can be generalized also. Okay. Okay, there's so we talked about the theory of K-means, and hopefully this is somewhat clear, and we'll see how we can perform using the software. So I have written R code and I'm going to show you. So what is the strength of K-means? Well, K-means is very simple. Uh, it's easy to understand. As you can see, it's very easy to understand and very easy to implement. And it's also very efficient. It's the linear. That means when you have large data set, the performance is quite important. Many times, the algorithm can take a lot of time. Many other algorithm can take a lot of time. So since this is linear, this is much better when you have large dimension, and it's just very popular. But there are some weaknesses as well. The algorithm is only applicable if the mean is defined, and many times your mean wouldn't be defined, especially when you do not have the numeric data. In that case, you won't have a mean, right? So k-means is not applicable in those cases. The user needs to specify k. So you have to be an expert in the data that you are working on. That means you should know how many clusters are there in your data. You cannot afford to have this from your algorithm. The clustering algorithm will not tell you how many clusters are there in your data. You just have to provide whether it's k2 or 3 or 5 or 6, whatever. The algorithm is very sensitive to outliers. That means when you have extreme observations or observations which are very different from rest of the observations, then are very far away from other data points, then the algorithm doesn't perform well. We'll take an example to show you how that affects. So here is a typical examples of k-means algorithm not doing well when you have an outlier. So here you can see you have set of data points and we have another set of data points. Okay. Now, if you use k-means clustering algorithm in this case, and k equal to 2, let's say, it combines these many data points to be cluster 1 and the other data point set of data points to be cluster 2. But ideally, this is not a good clustering because one of the data point and this one is far away from the other data point. So that data point should have been removed, and then we would have got a much better clustering segment. Here in the second graph you can see if you remove this data point and build two cluster, you can see a much more clearer clustering, a much more elegant, much more clearer, right? If you just remove that, right? But here you can see these data points have been clubbed with this data point, which is they are very far away, but yet they are in the same cluster. That doesn't make much of a sense when you try to interpret. So it's very sensitive to outliers. So you should deal with outliers before using clustering. There are methods to deal with outliers. So one method is to remove some of the data points in clustering process that are much farther away from the centroid. That means just remove them, right? The way we did, we just simply remove them. We simply did not use this data point, and then the clustering is much better now. So that's one way. The second way is to take a random sampling. When you take a random sample, then you will likely to not include many outliers in your sample. Okay, so that's the second way of handling outliers. The algorithm is very sensitive to initial state. That's another weakness of k-means. Okay, so initial state means when you first or the algorithm rather first chooses the initial points, that will decide how the clustering will happen. Okay, here is a typical example. We have taken the same example, right? This is one cluster, this is another cluster. But let's, for instance, the initial data points have been chosen to be somewhere here and somewhere here. Sorry, somewhere here. The first one, the other one will be somewhere here, not this one. So in that case, the first cluster will be this one. It will take half of the first one, half of the second one, and you combine it as a one. In the second time also, then you recalculate the centroid, and the centroid comes out to be here, and then it doesn't change. Now you can see this is not a proper clustering. You are getting somewhat of a misleading clustering. Should have been like this one, right? This set of clusters and this set of clusters. So you can see not very clear clustering happening because the initial seed or the data point that was selected wasn't a very appropriate one. So that's a typical issue. This is a much better cluster segments than the other one that we just saw previously. Another important weakness of K-means clustering is that it's not very good unless you have hyper ellipsoid cluster segments. For instance, if you can see this one, there is two clear clusters, right? So this one is the cluster and the other one is this one. Very complicated, very non-linear form of clustering, but there is a clear cluster. Clearly the two different clusters, right? But what it does is that it takes the upper half as one cluster, it takes the lower half of the second cluster. Which is not proper, right? It is not a correct representation. So this is, unless you have a very clear shape of your data, then the clustering will be somewhat not appropriate. So here's an R code for doing K-means clustering. So you can in fact take this data and you can run it on your own. So iris data is what I have taken. Iris data is available on R. You can just use it. You don't have to import it from anywhere. So iris data has got the data for flowers. There are three different categories of flowers, and then their petal length, then petal width, sepal length, and sepal width. Okay, so these four attributes of the flowers have been given, and then using K-means clustering, we are trying to see whether we have these three segments of flowers or not, and then we'll try to see if the actual segments for three different types of flower is similar to what the clustering algorithm has given us. Okay, and then we'll do a comparison. Okay, you can run it on your own. So here is a code. So we use K-means function, and we have taken four attributes from the iris data to do this. You can run this, and then you can validate using the actual clusters and the predicted cluster, and to see how well this algorithm does. You can take this code to the R and run it by yourself. There is also a video in the description section where I have performed. You can also watch that video to understand how we can do it on R. The next thing that we'll study is hierarchical clustering. Philosophically, it's different from K-means clustering. Okay, it looks much better when explained with the help of a graph or a tree rather, and we call that as a dendrogram. Okay, and we'll try to understand how we build this dendrogram because there are few steps involved, and then we'll see how it actually helps on understanding how many clusters we have and what the clusters are. So we don't have to provide explicitly how many clusters, the value of k, the way we used to do in K-means. Rather, the clustering algorithm will help us understanding how many clusters, actual clusters, are present in your data. So you need not know how many clusters are present a priori or before you use algorithm. So that's one advantage over K-means. So there are two types of hierarchical clustering. One is agglomerative, which is also known as bottom-up clustering. So it builds the dendrogram, the one that we saw in the last slide, from the bottom level. Okay, and I will talk about it, what it is. The second one is the divisive clustering or top-down model. It starts with all data points with one cluster. So I'll talk about it, how it's different. Okay, so that's very easy to understand. Okay. So in agglomerative clustering, it builds the dendrogram from the bottom level, and it merges the most similar pair of clusters. Stops when all data points are merged into a single cluster. That means, let's say we have, let's say there are 10 data points. So it takes each data point as a cluster. So this is agglomerative clustering, okay, or the bottom of clustering. Okay, each data point as the cluster. So if there are 10 data points, there are 10 cluster. N data points, N cluster. That is iteration 1. The iteration 2, it combines the next closest cluster. So these are two closest, it combines and forms one cluster. These are two closest cluster, it combines and form another cluster. These are two clusters, it combines, forms another function. These two, and so on. Okay. So now from 10 cluster we have got 5. From 5 we'll have 3, right? Because 2, 2, and then 1 will be another cluster. From 3 we'll have how many? 2. From 2 we'll have 1. Okay, so till the time we have that one cluster which combines all data points, this algorithm will run. So there is a fixed number of steps involved in this. Unlike KMeans, where you cannot calculate what is going to be the fixed number of steps, here you can easily calculate what is going to be the fixed number of steps. It depends on what's the number of data points, right? Depending on the number of data points, we'll be able to calculate this very easily. All right. Now, once we have this, we try to create a decision tree type, graph that we just saw in the last slide, which is called a dendrograph, right? Simple, right? The first observation is now taken as a one cluster. This is one cluster. This is one cluster. This is one cluster. Now these two are close, so we combine this one. These two are close, so we combine to form this one. Now this one and this sixth and third have been combined to form 8. Whereas for 6 there is nothing, so 8 and 6 have been clustered into 9. Right? It's very easy. From bottom we are going up, so that's why I call it bottom up. And how many clusters do we have? Well, we can take this entire segment to be one cluster and this entire segment to be one cluster, two cluster. We can also have three cluster also, right? We can take this one as one cluster, this one as second cluster, and this one as third cluster. So depending on what is best suited for us, depending on our analysis, we'll be able to know what exactly is the number of clusters and which data points belong to which cluster. The top down is exactly opposite. You start with all data points and start breaking down into smaller clusters till the time each data point is a separate cluster. It's exactly opposite of that. So whatever I've just demonstrated, it's just written in different points. At the beginning, each data point forms a cluster, also called node. Merged nodes are cluster that have the least distance. Okay, the closest distance, the closest clusters, you just merge them. Okay, and you keep on merging in each iteration till the time you have just one cluster, and then you form the dendrogram. Okay, you just form the different steps how you kept on merging. Okay, and then you decide how many clusters you want, and when you decide that, you can easily calculate. You can easily find out which observation belongs to this cluster. It's very easy. Just by looking at the dendrogram, it's very clear. Here is an example. Okay, so there are how many? Well, there are 5 data points. Okay, P1, P2, P3, P4, and P5. Okay, the first step, each P1, P2, P3, P4, P5 with the clusters. The first step we had 5 cluster, right? P1, P2, P4, P3, P4, P5, right? And P1 and P2 are close, very close to each other, right? The least distance. We calculate the distance, every time in cluster we are calculating distance. Hence we will study more about calculating distance. How do we do that in the next few slides? So we calculate distance between P1 and P2. That happens to be the least. So we combine them into one cluster. Here also P4 and P5 are close, so we combine them into one cluster. P3 remains alone, right? So there are now 3 clusters. In second iteration we have 3 clusters. P1, P2 in one cluster, P4, P5 in another cluster, and P3 in a separate cluster. So it's cluster 1, cluster 2, and cluster 3. So 3 cluster now. In iteration 3, P1, P2 is cluster 1, right? So this cluster 1 and cluster 3 are very close, right? Again, they have been merged. So we merge now. So now we have 2 clusters, P4, P5. So this is one cluster. P1, P2, P3 in a single cluster, so two clusters, right? So these two have been merged, so we have P1, P2, P3 in one cluster and P4, P5 in another cluster. Alright, in the final state we just combine everything, so we just have P1, P2, P3, P4, P5 in one single cluster. Simple, right? The way you started with each point to be a cluster and then started merging points to form, a bigger cluster and so on. You just build similar diagrams, right? P1, P2 separate cluster combine to form another cluster. P3 separate cluster combine with become this cluster. Here P4, P5 combine to become cluster 2. Cluster 2 and cluster 3 become cluster 4. Simple. So looking at the dendrogram, it gives a lot of good insight. We will know how many clusters do we want it finally. So measuring the distance is a big issue in clustering. We need to know how do we calculate distance, and there are many methods to do it. One is single link, complete link, average link, centroid. Well, let's go through as to how do we calculate distance between different points, because that's what matters to us. Whether it's K-means clustering, whether it's hierarchical clustering, we need to find out the distance between the data points. In single link method, the distance between two clusters is the distance between the closest data points. Okay, so here is the cluster 1, this is the close cluster 2. The distance between these two clusters is the distance between the two closest data points. If this is a data point and this is another data point, they are very close, right? So this distance, let's say this is distance d, so d is the distance between cluster 1 and cluster 2, because these 2 points are very close, and whatever is the distance between these 2 points, we will consider that as the distance between these 2 respective clusters. Now this is one way of calculating. The other one could be, we'll take exactly the opposite. So we will take the 2 farthest data points. So 2 farthest data point, one is here, the other one is here, right? They are the farthest to each other. So whatever be the distance, okay, we will call that as the distance between the two cluster 1 and cluster 2. Now you can see the way you take the distance between two clusters, the clustering algorithm partition the data accordingly. You can see the whole lot of this data has been clustered into cluster 1 and a small section into cluster 2. On the other hand, if you take complete link method, where you take the farthest data points to be the distance between two clusters, you see one set of clusters data points are here, the other set is here, right? So that's somewhat different from what we have seen in the previous slide. So depending on which method the algorithm is using to calculate the distance between two clusters, you will get different. Average link is just averaging it out. Instead of taking the extreme points, whether it's closest or farthest, right? Closest or farthest, in average link, you take the distance between two clusters is the average distance of all pairwise distance. This is to be kept in mind. All pairwise distance, okay, between the data points in two clusters. You take each data point in cluster 1, each data point in cluster 2, calculate pairwise distance. For one data point, you take distance for every other data point in the other cluster, and for second data point, take distance for every other data point in the second cluster, and you take the average of that. Whatever is that average, you take that as the distance. The centroid method is that the distance between two clusters is just the distance between the centroid, which is very simple and easy to calculate and also quite easy to understand. You take the centroid of each cluster, and whatever is the distance between these two centroids of the respective cluster is the distance of the cluster. Alright, so we'll now talk a little more about the distance function. We'll then talk about data standardization. Well, the distance function is used to find out the similarity and the dissimilarity. Okay, we are interested in finding out similar observation which can be put into one cluster, dissimilar observation which can be put into different cluster. Now there are different types of data you will receive. One could be numeric data, which is more of a continuous data. There could be nominal data, which could be more of a dummy form, or ordinal data, and so on. In such cases, you will have to have different way you have to handle. I mean, the algorithm handles, of course. You don't do it when you use the software, but the underlying algorithm will deal differently depending on the type of data. The most commonly used functions are Euclidean distance, Manhattan distance. Okay, this is the generalized form of a distance formula calculations. The h can take any values, right? So if it is h equal to 2, it is an Euclidean distance. So this is an Euclid distance of finding out distance. If it is equal to 1, then you get Manhattan distance. You take simply the modulus of the difference of the data points and take the sum. Weighted Euclidean distance is also possible if you want to give different weight to different observation while calculating distance. So that's also possible. Now you could also have binary attributes, okay, values, let's say 1 and 0. Some cases where you have values like 1 and 0. For instance, example, let's say male has been denoted as 1, female has been denoted as 0. So in that case, how do you calculate distance? Because the distance makes sense in continuous data, but how about binary data or categorical data? So what we use is the confusion matrix to calculate the distance. So how do we do that? We take the ith and jth data points. Let's say they are xi and xj, which are in vector form, by the way, because it has got different values. And then you calculate how many times you have xi taking a value of 1 and xj taking a value of 1. And the number of times, let's say, is a. How many times xi is 1 and xj is 0? Number of times is b. And how many times it is xi is 1 and xi is 0 and xj is 1? Number c. And when both are 0, it's number d. Now, when both are same, it is similarity, right? So the first matrix, so first this one and this one are the similarity when both are 1 or whether both are 0, which is a plus d. So this is similarity. B and C are when they are dissimilar. That means one is like xi is 0 and x1 is 1, or x1 is 0, xi is 1 and xj is 0. So they're dissimilar, right? They're not similar. So that is dissimilarity. So dissimilarity is nothing but the distance. C plus B is the distance. So that's the way you calculate the distance between binary variables. In nominal, if it's a nominal variable, that means it has got more than two categories. In that case, it's simple to calculate. It's just a more generalization. You take the total number of categories, let's say that is the R, and you see wherever there is matching cases. That means here you can see matching cases, right? A plus D where they are similar, right? Same. Both are 1 1 or both are 0 0. Similarly, when you take various nominal values, right? Let's Q be the times where they are both same. So take it out from the total number and divide it by the total R. So if R is the total number of total number of categories minus total number of times when they are matching, and then divide by total number of categories. That's the distance. Data standardization is important. So how do we do data standardization? Why it's important? Now consider the following pair of data points, and we'll see what's wrong with the way if we use raw data in clustering. So here is xi, which is 0.1 and 20, and xj, which is 0.9 and 720. So the distance is 0.9 minus 0.1 square, 720 minus 20. So that's the Euclidean distance, and we find it out to be 700.0057. Now you can see that the 700 that we have found out, the distance, is majorly because of the second term, right? The first term doesn't contribute much. That means it seems to be a biased thing, right? It seems to be biased. That means the second term is contributing the most to the result, and the first term is not at all or hardly contributing anything. So it depends on the scale. The reason is because many attributes, I mean, whatever number of attributes, whether it's length, breadth, height of somebody, income of somebody, they are all in different scales, right? So you cannot use different scales of data to, do clustering or calculate distance. You rather have to standardize to ensure that they have common range, common mean, common variance, standard deviation, and so on. So to do that, we do standardization so that this, scale effect is minimized. So important is to reduce scale effect. Alright, so how do we do that? The popular one is to take out the mean and divide it by standard deviation. If the data is, let's say, xi, you take out the mean, subtract the mean of xi and divided it by the standard deviation of xi. Okay, so that's the way you calculate the scale values of your observations. The next thing we'll see is how do we select which clustering algorithm is to be used. We studied about a few of them, three of them in fact. How do we select which one works best for a given data? Well, it's very difficult, frankly. Unlike your supervised learning, where you can do validation of algorithms and find out which one works better. Like if you're using a linear regression, you can calculate R square, you can calculate a root mean square error, right? And then find it out by comparing across different algorithms and see which one gives the least mean square error or which one gives the maximum R square value. Whereas in clustering, we do not have a level data. We cannot compare it with, the actual, segments or actual clusters because we do not know what these clusters are. So choosing a best algorithm is always a challenge. So each algorithm has limitations and it depends on the type of the data distribution. So one algorithm could do well with a particular set of data, and you need another algorithm for another data set. There is no thumb rule as such that K-means works better than hierarchical or hierarchical works better than K-means. And there is no hard and fast, there is no thumb rule or there is no clear-cut way to decide which one works better. But how do we come to know that which one works better? There should be some weight, right? So the typical ways is that to run several algorithms. Okay, do not use just one algorithm to cluster your data. You use several clustering algorithms, and then the way you interpret is you just look into the clusters or look into the segments that the cluster algorithm gives you, and then you talk to your experts, take their opinion and see if the clustering is fine or not. They will give you an idea whether the clustering is which algorithm has done the best clustering. So it's always it's very application oriented and dependent on the expert's judgment, and it's very subjective. And that's why clustering algorithm is not just in science, it's also an art where your expert judgment uh, you know um, do contribute towards your model building. Cluster evaluation. As we have already said, it's very difficult to know the quality of a clustering. It's very difficult to evaluate. Okay, but there are few ways, not very robust ways, but somewhat crude way of evaluating. So one way is use some supervised methods. Okay, let's say you have we gave this example, right? A flower classification. There are three types of flowers, and we have given their length and width, right? Sepal length, sepal width, petal length, and petal width, right? Now you do your clustering and then find out the three clusters. Now take a small sample of supervised data where you have already some labeling. That means you already know which flower is this one. Now this is a very difficult thing. You will not get level data in many instances. But if you have thing, then you try to compare it with your clustering algorithm output. And then you will get to know which algorithm works the best, or whether it actually does a good job or not. But that's also unrealistic many times because you won't have level data to test it. If you have, let's say, just 10 to 20% of the data which is leveled, and many times you might get 10 to 20% of your whole data to be leveled, in that case you can do the comparison, not a problem, you can do. But even getting 10-20% of the data is also a big challenge. And then you compare with many of your matrices, like whether it's your R square value, the rate mean square error, whether it's your concordance, whether it's your entropy or precision, or F score, chi-square, and whatever be your metrics to evaluate some the ability of the model to classify your data, you can use. But the thing that is to be remembered, that the real world data for clustering, you hardly will get class levels to test. So that's why it's quite a challenge, and hence expert judgment is always taken while finding out the quality of clustering. Okay, so evaluation also can be done through internal informations. Okay, so let's say you do not have availability of level data to use some sort of a comparison. So what you can do is that just to see that the sum of the square of error. So you see that how near the data points in a cluster are to the cluster centroid. So you measure how near the data points at the cluster segments, and you also see how different are the cluster centroid from the another clusters. Okay, so basically you calculate intra-cluster cohesion or intra-cluster distance, and inter-cluster separation or intra-cluster distance. Okay, so the first slide I talked about, right? The distance between this is centroid here, this is centroid here. You calculate that each point, right, distance between each point to the centroid, and you also calculate the distance between the corresponding centroid, okay, of two different clusters. And then you see which algorithm gives the minimum of intra-cluster distance and maximum of inter-cluster distance. The one that gives the maximum inter-cluster distance and minimum intra-cluster distance is the one to be selected. Okay, so that's one way of comparing also. But again, expert judgments are quite helpful, so that's one thing to be kept in mind. Okay, so we have now come to the end of this lecture. We have gone through the various aspects of clustering. Few more things just to summarize what we have learned so far, and just if I were to summarize in few points, I would summarize like this. Clustering has a long history, and there hasn't been much success in clustering. A lot of success in supervised learning, and a lot of advanced things has happened over these many decades. But clustering, even after having a long history, we haven't seen much of success. Because obvious reason, because there is no level data for validation, and that's why it's such a hard thing to do. So it's very application oriented, and it is very subjective, and it all depends on if you have thorough expertise on the data, then using clustering makes sense. Otherwise, if you don't understand the data, then it's not very useful, because your output, your analysis will be very black box. You won't be able to interpret it very correctly. That's why domain skills are quite important when you are working with unleveled data and using clustering. So hope we have found this lecture useful, and if you have liked it, please like, please comment, and please share it with your friends and your colleagues. If you haven't subscribed to our channel, please do subscribe. Thank you so much.